I'd like to introduce our guest speaker today. Is Dr. Stanley from the University of Central Florida. He is the inventor, one of the inventors of neuroevolution of augmenting topologies, or NEAT, hyper-NEAT, and novelty search algorithms for evolving complex artificial neural networks. His main research contributions are in neuroevolution, i.e. the evolving neural network, generative and developmental systems, coevolution, machine learning for video games, and interactive evolution. He's an associate editor of the IEEE Transactions on Computational Intelligence in AI and Games, on the editorial board of Evolutionary Computation Journal, and on the ACM SIG-EVO Executive Committee. Let's welcome our speaker. I got it. Is that good?
Yeah.
Is it good?
Okay, well, thank you for having me here at Oakland. I appreciate everyone's hospitality. Hopefully I repay you with a good talk. And we will talk about evolving artificial neural networks for video games. So ACM asked me to insert this slide to acknowledge that this is the part of this is supported by ACM through the Distinguished Speakers Program. So we can be thankful for ACM. Okay, let me start by asking the natural question, which is, why would we like to talk about this at all? Why should we be evolving neural networks for video games? Now, a lot of people think about this. If they've heard of neural networks or heard of evolutionary computation, which is just basically forms of artificial intelligence, think about, well, what is more advanced AI going to contribute to video games? And the natural answer might be, well, maybe neural networks could control the non-player characters, or the characters that are in the games. And then they could be smarter or something like that. But I want to think about this a little bit more deeply, because why do we really need neural networks at all? I mean, classic game AI is good enough as it is, right? I mean, the kinds of algorithms that are used in video games, like scripting, A-star, pathfinding, finite state machines, some of these things you heard of, these are kind of classic algorithms that are used in the commercial world. They work fine. I mean, there's no problems. They're selling millions of dollars of games. No, there's a huge problem with the AIs of the games. And furthermore, neural networks, they have to learn. I mean, that's part of what neural networks are about. They're about an algorithm that allows a computer to actually learn. And so, what if they learn something bad? I mean, how do we know this is actually going to be fun? What if they get too smart? I mean, it's not necessarily fun if they start to beat you every time. You don't necessarily want to be playing against the world chess champion when you're playing against a chess computer. So, really we have to think a little bit more carefully about why this is such an exciting idea. It's not necessarily the obvious thing of, well, we're just going to have smarter characters. That's not, at least in my opinion, where the exciting aspect comes in. What is more exciting is that evolving neural networks and similar technologies opens up entirely new game genres. And this is where it's more interesting. So it's not just about making non-player characters smart, which, okay, that's interesting. But maybe not the most interesting thing, because if a game can learn and create, because after all, those are typical aspects of evolution. In other words, evolution, if you think about evolution, I'll tell you a little bit about it in a moment. It's a creative process, and it creates forms that maybe no one would have thought of before. So we have this concept that the game from neural networks could learn and through evolution could create. Then new things become possible, things that you really cannot have with current technologies. Like, for example, the player could become like a teacher and teach agents in a game. The game could invent its own content instead of artists and designers. Players could breed and trade content themselves. All of these things could potentially become possible if this kind of technology was put into games, and they simply are not possible at all without these kinds of technologies. And so you see these kind of screenshots here of some of the games that I'll show you that actually do all these things, and so you'll see what these technologies open up. Okay, so Now, let me go in a little bit of a different direction. I want to explain to you what evolving neural networks is, so that everybody kind of is at the same level of understanding of what I'm talking about in terms of the technology, the underlying technology. Some of you know more about this than others, so bear with me for a moment so I can get everybody up to the same level. Evolving neural networks is an area of artificial intelligence. It's an area of machine learning, which is also called neuroevolution. So neuroevolution just means evolving neural networks. And artificial neural networks, which are often called ANNs, so I'm going to use that term, ANN, you can think of them as tiny artificial brains. They're a little bit like brains. They're motivated by brains, they're inspired by brains in nature. So we can think of them as little brains that can control artificial agents. And so they can do things like brains, like sense the environment, like the way that you do. Your brain senses the environment through your sensors, like sight and sound. And they can act, like control the motor control, arms, legs, talking, those kind of things. So can artificial neural networks do these types of things. So evolving artificial neural networks is a special way of training artificial neural networks. Some of you have heard of traditional neural network learning algorithms like backpropagation. Usually when people hear the word neural network, they think backpropagation, they think anything. But that's not what I'm talking about. I'm not talking about classic neural network learning algorithms. I'm talking about breeding them. So that's where the evolution part comes in. In other words, our brains came from evolution, right? And we are descended from predecessor organisms who had simpler brains than us, and ultimately back to ancestors that had no brains at all. And so brains are something that emerged from an evolutionary kind of Darwinian survival of the fittest kind of process. And we can do that in a computer too. You know, why not? And so we can, in a sense, breed artificial neural networks, like artificial brains, like we would breed animals. If you think about animal breeding, it's nothing so complicated. You can imagine breeding horses to be faster or something like that. We can breed artificial neural networks in a similar way, and I'll show you a little bit more detail how that could possibly be. But in this case, we'd be breeding these little brains themselves. And this is a form of what would be called evolutionary computation. So causing evolutionary processes to actually happen inside of a computer. And I'll show you some of that shortly. So let me tell you a little about evolutionary computation. This is the idea that we could do evolution in a computer. How would this happen? Well, if you think about natural selection, I put natural in quotes because obviously it's not natural if it's in a computer. But if you think about natural selection, this idea is basically an algorithm. Right? I mean, the idea that some organisms are fitter than others and those get to reproduce. So there's a picking process, there's a reproduction process. Selecting is picking the best parents. Variation through mutation and through mating to combine the genetic material of two individuals to get an offspring. This could be formalized as an algorithm and actually run inside of a computer. So how would it get started? That's the big question. I mean, in nature, in science, biology, I mean, it's a big question. How could evolution have gotten started? It was a single cell somehow like floating in a chemical soup one day. But in a computer, because it's computer science, you don't have to worry about answering kind of philosophical questions of where does life begin. We can just start with some really bad individuals. Basically start with random genomes, random DNA, basically junk. Now, that's different than nature, presumably we should start with something completely random. But we don't know how to start, so we can start with something random. But this can still work, even though we can imagine a bunch of kind of garbage floating around in the computer. But some are going to be better than others, just because of statistical variation. Some things are better than others. And if you force this kind of survival of the fittest competition onto that population of artificial organisms, say the ones that are better, we can measure how their quality, the ones that are better get to reproduce, then this leads to this kind of a competition, and progress will occur over generations. So you can bootstrap this kind of process inside of a computer. So this is just to motivate this idea. I don't think anybody's ever actually tried to evolve something around. It's probably not worth anybody's time. But this just gives you the idea of how this could work, why it's very algorithmic. Imagine we call this generation 1. And what these are, this is a randomized population, so just a bunch of random blobs. Now imagine that what I want are things that are round. So what would I do? I would just, from this group, pick from among them the ones that I perceive to be the most round. And so maybe these two look rounder than the others. This is just pure statistical variation, it's just chance. And I pick the ones that look rounder, and I say, okay, well, they're going to be parents of the next generation. So I let these two effectively mate with each other and have children, and here are their children. This is called generation 2. So it's a new generation of blobs. And you can see that, on average, they're rounder than the parent generation. Well, it's not surprising because we didn't let the least rounder ones reproduce. So these are a little bit rounder than their parents. And in fact, some of them are rounder than the most round in the previous generation. You know, you might argue that, like, for example, this individual is rounder than this one, or this is one of the ones before. And that'll happen occasionally. You know, sometimes you'll have a child that's not as smart as you. And sometimes you'll have a child that's smarter than you. And sometimes you'll have a child that's about the same intelligence. You know, guarantees either way. But if you have enough children, eventually you'll get something that's a little bit higher on whatever scale you're interested in. And so over time, this kind of thing is essentially inevitable that you're going to get some improvement along this gradient, in this case roundness, and then we just play this game again. So we say, okay, these are the roundest now in this new generation, so these two can be parents, they're going to have children, and here's their children. And so it's another generation, and they're even rounder than their parents. And here we found somebody so round that you can't get any rounder. We just call that the champ. So commonly, that's the name that we would use to describe someone who's as good as you can get or as good as we care for anybody to get. Sometimes there is no concept of a champ. You're not trying to achieve it. If you think about evolution in nature, there is no such thing as a champ here. One person in this room is the best, and everybody else is not. But it's sometimes in some domains of roundness, there actually is a champ. So this is the kind of process that we could imagine automating inside of a computer. Now, you can imagine that that's an algorithm. We can do that with like anything that we want to optimize. We can imagine optimizing through evolution. But what we're interested in here is evolving neural networks, and that's where the neuroevolution comes in. So instead of evolving roundness, we will evolve neural networks. And the neural networks that perform better in the task, depending on what task it is, and you'll see several kind of tasks, but in this case it'll be in video games, are chosen as the parents of the next generation. And the offspring neural networks may perform even better, just like the offspring blobs sometimes are rounder. So now what I want to do is so that you understand what this means. Because it sounds, if you haven't seen a neural network before, it sounds rather abstract, talking about we're going to be picking brains out of a population. Let me just show you briefly a little bit about what a neural network is. And so these are the things that we're going to be grading. So again, just bear with me if you're familiar with this. Get everybody up to speed on the same topic. So here's a neural network. This on the left. Now, of course, it's motivated by biological brains, like this thing which is in your head. And here's some neurons, and this is what they actually look like. These are cortical neurons. So biological brains, of course, are made out of neurons. And the neurons send signals to each other. And so the idea is that we could simulate this process inside of a computer. We could create these nodes which send signals to each other, which go over these lines, or connections. And if we attach them to each other in the right way, then they may perform a function that is useful to us in some way. Just as a brain performs a function, it essentially is also a connected network of nodes. So, how do they work? Well, the first thing that's really important is that they have inputs and they have outputs, just like we do. Like you said, we have our sensory input, which includes things like seeing and hearing and taste and touch. And so that comes in from the body and is eventually, ultimately, ends up coming into the brain through some interface. And eventually, the brain does some processing and then it makes outputs. And the outputs control something. In the case of a human, it controls your body. It makes your body do things. An artificial neural network is the same kind of idea. It has inputs, what you might call sensors. They come in, so we'll feed them in through the computer. The computer will feed them in. The computer program will do that. They go through some processing, some internal processing, and then eventually those signals are sent to the outputs, and the outputs decide what it will actually do. Now obviously, the really interesting part is in the middle. How does it do this just processing? Obviously, that's no small thing. The processing is everything. That's basically who you are. And so in the middle of this network is where it makes its decisions and embodies its intelligence. So, like, just to help you to see, like, how does this connect to anything real or concrete, especially like a game? you can imagine something like this. We could literally hook up a neural network to control this car in a simulation. It's like a car in a video game. You can imagine that. The neural network would input what the car sees in the front, left, right, and back. In terms of seeing, what I mean here, like it might just be that it projects like a ray out from its front and just sees where it hits. And so this front sensor, this thing here, would just be a single floating point number, like a distance. And it would be the distance that that ray went out from the front until it hit something. And like left could be similar, like I could imagine that it's projecting the ray to the left and see where it hits, and that might tell it where the border of the road is. So we're talking about very, very impoverished input compared to like your eyes, which have millions of photoreceptors, and the resolution of your eye, compared to like this thing, which has only literally four floating point numbers coming in. And then the output would be like steering commands. Like in this case, forward is like the gas pedal, and left and right are like the steering wheel. So literally kind of say, we're given some rangefinder sensors that can sort of project rays out and see what's out there. And then on the outputs, we give it basically a steering wheel and an accelerator and say, okay, you decide what to do, and then let it go and see what happens. And of course, like once again, the important question is what happens in the middle. It's got to make intelligent decisions, so some processing goes on in here. That's its brain, so to speak, where we'll be making its decisions about how to drive the car. But what this shows you is that, yes, we can insert these kind of neural networks into basically anything we want. We can decide what inputs go in. Obviously, we have to pull those out of the environment. In this case, it would be a racing game. And then we have to feed them in and then ask the neural network. The neural network gets to decide what to do. So what does happen inside the neural network? And this is the only equation that I'm going to show you. But just so you have the basic understanding of what is this kind of thing like. It's actually a really simple idea. I don't want to go into a lot of technical detail, but I wanted you to just have an intuition, like what does this thing do? Basically, what is going on is that the inputs, you can imagine them as taking in information. And then that information flows up through the network to the outputs. You can almost think of it like an electrical circuit, with the information here, in this case, flowing over these wires, you can think of it as. And so basically, like whatever comes in on this input, which we call X1, would go over these wires, W11, which goes to hidden node 1, and W12, which goes to hidden node 2. And these W's, what they mean is that there's weights on those connections. So some connections have a higher weight than other connections. That is what gives this its functionality, its unique personality will ultimately turn out to be the weights. So there's different types of things are emphasized differently. Now, just if you want to have some intuition, like what does this actually mean? It's so abstract, it's just a bunch of numbers. What does it actually mean to have these weights? Well, you can think of it as something like if there was some neuron that told you whether there was a ball flying at your face, you know, say that this neuron is the ball flying at my face neuron. So it's a sensor and it detects that. Then you can imagine that if there's something that eventually connects to like a duck output, well, probably there's going to be a high weight there, right? If this is a good functionality, it's going to say, I want to connect having a ball flying at my face to ducking. And so ultimately, these do have some kind of meanings because there is some semantics to the inputs and the outputs. And the hidden nodes are performing what you might think of as sort of complex intermediate functions to decide like what these inputs mean, because of course it's not always so simple as just is there a ball or is there not a ball, in order to make a complex decision. So these intermediate nodes are performing functions, or sometimes people talk about like feature detectors, like it may actually detect that there is a situation that you need to be aware of and therefore send some signal to the output that says, okay, now you need to duck. Now, just formally speaking, what is the actual function that's performed at each one of these nodes? It's the same function at every node in a classical neural network. Of course, there are many neural models, and I don't want you to think this is the only one. This is just kind of a traditional one. A lot of the time, people will say, well, neural networks, they're not really like real brains. Well, obviously, this is not a real brain. I mean, it's way oversimplified. Even a single neuron in a real brain is more complicated than this whole system. But we can make it more or less complicated arbitrarily. It just depends on what we want to do. There's no limitation on what we can do here. But this just tends to be a traditional way of doing it and sort of gives you a sense of how they work. So basically, the idea is that we have to somehow formalize the idea that each one of these nodes, every node, other than the inputs, will take in information from the previous layer over these weights. And that's what this expression formalizes. So it basically says that at hidden node J, it will sum up, and that's what the summation is, the incoming signals x sub I, which are basically these in the case of these hidden nodes, the x1 and x2, multiplied by their weights. So in other words, x1 is multiplied by w11 and arrives at h1. and x2 is multiplied by w21 and arrives at h1 as well. Those two things are summed, and what we could call that summation, you could think of it as that's the incoming activation. That's how much activation is coming into that location over its connections. And then, finally, traditionally, that will be run through something like this thing, which is called an activation function. In this case, it's a sigmoid function. So usually, the incoming activation is run through some kind of sigmoid, which is a squashing function, which causes it basically to squash into something that looks like this. So in other words, if activation is really, really high as it goes towards the limit, like along x, this is the level of incoming activation along x, this asymptotes, so it never goes above 1. And if it's really, really low, like if it goes negative, and it can go negative, then this also asymptotes at 0, so it never goes too low. So basically it keeps it so it's within some bounds. And if you think about it, that makes sense intuitively as well, because neurons in your head can't fire at an infinite level, right? I mean, there's some physical limitation to how high their activation can get. And so the sigmoid kind of captures this idea that the farther the incoming activation goes to the limit, the more this thing just starts to threshold out and not be able to get any higher. Now we can have positive weights, but we can also have negative weights. Negative weights like represent the idea of inhibition. Like this node inhibits that node. So inhibition obviously is a big part of intelligence too. And positive weights you could think of as excitation. This concept excites that concept. Okay, so the same thing will happen again at the output. So these will basically sum up their incoming signals from the hidden layers and so forth. And this could go on indefinitely. We could have more than one hidden layer. We could have any topology we want. We're not limited. We could even have feedback connections that go backwards from outputs into the hidden layer. But this is just a really simple model to give you an idea. So you have a concept of what this is doing. But the big question here, the big question is, what should be the topology of this thing to get it to, like, say, drive that car? We don't know. Nobody builds these things by hand. At least nobody sane does that. Or doesn't do that. What are the weights that work? This way, these question marks. You know, we don't know how to build anything. Like, what should this be to make this thing drive? And so the usual idea is that neural networks are not things that you build. Neural networks are things that build themselves. In other words, they can learn. And that's how they get their internal weights and their internal nodes and become able to do things you want them to do. And neuroevolution, what we've been talking about, this idea that we could actually evolve them, breed them like animals, is a type of neural network training algorithm which will answer these questions and basically cause these things to evolve on their own so you don't have to. So this is like what the loop would look like. What we can do is, you can imagine, is create a population of random neural networks. In other words, like random ones of these things. Random weights. Maybe random connectivity. Maybe random topologies. And then loop. And in this loop, what we would do is we would say, we're going to take everybody in that population. Say there was 100. We have 100 random networks. They're not going to be very good at anything because they're random. So you take one at a time and put it inside of the body of whatever it is that you're trying to test. So it could be the car, just for the sake of example. Imagine it's the car. So you take that neural network, put it into the car, and then you say, okay, I'm going to let you go and do your thing. So we're going to feed the sensors in, look at the outputs, let it drive, and see what happens. It'll probably crash or something because it's random. But we do that for every one of these 100 individuals. Take it, put it in the car, let it drive until it crashes, or perhaps for some limited amount of time if it doesn't crash. Then take the next neural network, put it in the car, see what it does. Eventually we've got 100 different things that have been tested. We have a score for each one. And we say, how well did it perform? And that's what's called the fitness. So that's the fitness. And the fitness allows us to know which ones did better than the others. And this is all completely up to us what we care about. And what does it mean to be fit? It could mean being fast. It could mean being reliable. It could mean being both. It could mean crashing. Maybe we want them to crash. It depends on what we want. But we can define how we want, and they will train to become that way. And so from the fitness, however we scored them, we select the better individuals. Now these are these artificial brains. And then we mate and mutate them to form a new generation of neural networks. Now that's the part, it sounds a little strange, mate and mutate a neural network. But it's just, you know, you can imagine that there are ways that we can combine like this thing with this thing in some kind of parsimonious way that would give us something that makes sense. And there are algorithms for doing this. They're neuroevolution algorithms. So we can combine these things, and that's basically they have a child, and the child can resemble both parents and so forth. And so we can mate them, and we can mutate them, like slightly perturb their weights. And that's the next generation. So we selected the fittest. They had children. That's the next generation. Then we repeat the loop again. All of those guys get put into the domain, into the car. They get tested. Then we repeat. And so what will take hold is this kind of Darwinian survival of the fittest situation. Things will get competing to survive in a world where in order to be good, you have to drive fast. And they will get better at driving fast if that's the kind of pressure that's on them. So the brains will actually become able to drive cars, even though nobody knows how to build a brain that drives a car. So I mentioned this particular algorithm, Neuroevolution of Augmented Topologies. This is from my PhD dissertation, but it's worth mentioning because it's inside of all of the games that you will see in this talk. And this is probably this is the most widely used neuroevolution algorithm today. There's a lot of public versions of this that you can get. And so it's freely available, and you can use this if you find the topic interesting without having to build your own system from the ground up. But what distinguishes NEAT and why it's interesting and why I want you to know what goes on in this system is that it doesn't just decide what is the optimal weights or what is the optimal topology. It actually makes the neural networks get increasingly complex over generations. And how that would happen is that sometimes mutations occur that add new nodes or new connections that cause the network to basically get bigger. So you can imagine that a new connection appears, and so now we have more connections, and then in the next generation, more connections. I want to emphasize that this happens over generations, not over an individual lifetime. It's not like an individual is out there driving a car and their brain is expanding while they're driving. It's that individual has a child who has a bigger brain. And then that individual has a child who has a bigger brain. Now, it doesn't always get bigger, and bigger is not always better. But the point is that bigger means that there's a potential to be more complex. It's not a guarantee, it's a potential. And so gradually over time, evolution will harness and take advantage of the increasing complexity. And that means that more sophisticated behaviors can evolve over time. And of course, this idea is appealing because that's supposedly what happened over actual natural evolution, right? I mean, the neural networks in biology got more complex. So we would like to capture that concept inside of an algorithm, so NEAT can do that. And that's what this diagram represents. It just gives the concept that you can imagine it starts with very small neural networks, which we call minimal neural networks. So this just represents that they're all really small. They have no hidden nodes at all. And over generations, the population kind of grows into a bunch of diverse topologies of higher complexity. And that's just what this is conveying. And so NEAT being inside of these algorithms means that inside of these games means that not only will behavior potentially optimize, it will also potentially become more complex, which is more interesting than just optimization.
Sorry, do you want to allow questions as you go, or would you rather wait?
Sure, yeah, absolutely, please.
So the question that comes to mind is, do they have a fixed number of children? And is there a relationship between how many children you allow them to have and how many generations are needed, or what's the trade-off?
Yeah, so there is a lot that you can say about those kinds of questions, and they're good questions, which I've completely glazed over so that in the interest of time. But since you've asked, yeah, I mean, in evolutionary computation, there's a lot of study of what are the most promising mating strategies, reproductive strategies, selection strategies. And it's a very non-trivial problem to choose parents intelligently. So like one thing you might think is just choose like the top 5 smartest or something. But that's not always a good idea because that would destroy the diversity of the population and it would quickly converge to something prematurely. So you wouldn't get continual aberration. And in fact, diversity is a very healthy thing for an evolutionary system. So there's all of these mechanisms that are inside of these algorithms that are meant to do things like protect diversity, so secondary goals. So there's no simple answer. So in other words, the individuals that reproduce will reproduce at different rates depending on who else is in the population. So some may have more children than others in one situation, but in another they might have less, and it can be quite complex. But it's all geared towards keeping evolution kind of a healthy situation. So it's similar things to what any breeder would be confronting, but on a much larger scale, since we're talking about potentially hundreds of individuals and thousands of generations, which is more than usually you're breeding with animals. So it's a complex topic. Does that answer enough to give you a sense of it? Okay. All right. So these are just so there's some applications that NEAT enabled. You can just see that these are balancing poles, driving car, vehicle warnings. This is a soccer, keep-away soccer. It played Go. It was controlling a hopper. It actually makes music. This is a duel between two robots. Just to give you a sense of diversity, so a lot of control applications, but not just control, things like music too. And so, you know, if you're thinking like, what can you do with an algorithm like this? Like, what are the limitations? Well, the limitations are that the same limitations as your brain. I mean, anything a brain can do, you can try to apply this to, because basically it's evolving brains. That doesn't mean it's as smart. I mean, I don't want to come off as like a mad scientist here. I'm not saying that they're really human brains. What I'm saying is that you can try to do anything that a brain can do. So that's why there's such a diversity here. That these things almost don't even seem to make sense together. It's because, well, we do a lot of things too. We do creative things, we do control things, and all of the things are things we could try to evolve with neural networks. All right, so now let's get back to the main topic. So you have some idea what's going on here. We're going to breed brains. And now what I've claimed to you is that this will enable us to do things in games that we could not do if we didn't have this technology. And so I'm going to show you a few games. So the first game I want to show you is called Neuro, or Neuro-Evolving Robotic Operators. And in each case, when I show you these games, we created these games for a purpose. And the purpose was to send a message to the game industry that they shouldn't just ignore these technologies, these exotic new technologies, because these technologies do enable things that the game industry will not be able to explore without these technologies. And the game industry is very conservative, actually. They do not like to experiment with exotic technologies. And I'm not saying that's necessarily a bad thing. I mean, it makes sense commercially. Why take risk if you don't have to? And they perceive this, that their AIs are working well enough. And that's why I said perhaps the reason to use this kind of technology is not to make the AIs better, so to speak, but rather the message is to create new kinds of games, and that do require these types of AI. So one of those types of games you can imagine is if you wanted the player to take the role of a teacher. Because after all, how can you be a teacher if you don't have something that can learn? So you want genuine learning inside of the game. In other words, the characters in the game get smarter because you teach them. Well, then there has to be a learning algorithm, like a bona fide learning algorithm. And so we could actually do this with this kind of technology. And so this will be really interesting because what you can do is you can do real-time evolution, like they'll actually evolve in real time before your eyes while you're playing with them. And to you it'll look like they're learning from you. And of course they are learning from you. But you don't actually have to know that it's evolution under the hood. So what is this game? So the game is that you're going to be, the player plays the role of a teacher or kind of a drill instructor in this case. And you're training a squad that's going to go into a battle. And so what happens is these non-player characters will improve in real time as the game is played. And so here's kind of a sequence you could imagine like doing. Like these little blue guys are the squad that you're teaching. And so you might say, okay guys, here is a turret. I want you to learn to attack it and not get shot. So it's like they're in kindergarten. They're starting with something simple. You can't teach them calculus when they're in kindergarten. So you start with something simple. Once they get good at this, you say, okay, great, good job. Now let's add another turret, make things harder for you. Let's see if you can deal with two of them. And once they get good at that, you can say, okay, well, we'll put walls in here. So now you're going to have to navigate around the walls and learn to attack and not get shot. And then we can say, okay, well, maybe we'll put wheels on the turret. So now they're actually roving around, making things a lot harder, and so forth. And so we kind of incrementally train them gradually to get smarter and smarter. This is what the player would be doing. So the strategy that the player is implementing is the actual curriculum, is trying to actually get these things to learn so that eventually you've got graduates, and these graduates go out into the world, and of course their world is a battle, and they will battle against another team that was trained maybe by your friend on the internet or something like that. And we see what happens, and then you see how good of a teacher you actually were. And if you weren't a good teacher, you could go, back to the drawing board and start over again. Or you could teach them further, give them more lessons. So the player gets to train the AI for a goal and style of play. This is just an example. It doesn't have to be this. You can imagine different ways. And you'll see a lot more when I show you the game. Now, one thing to keep in mind, I want you to keep in mind, because it can be confusing what you're actually looking at when you're watching this. Every AI unit, every robot that you see has its own unique neural network brain. It's not like they're all controlled by some group brain or they're all clones of each other. They're actually, each one is a unique individual, just like everyone here is a unique individual. And they're literally evolving before your eyes. And so, of course, the culmination, the payoff is when you go to battle. This is just a screenshot of the battle. And evolved behaviors will be saved when you're happy. And you can assemble your team of trained agents and then see what happens in the battle. And of course, these are like your children. You've been bringing them up since they were totally ignorant at the beginning. And so you've got some emotional investment there, hoping to see them not all die a painful death. And so let me show you what this game is like. Question, yes?
Do the agents learn from each other?
Do the agents learn from each other? They...
Or is there something in there where they could learn from each other?
Yeah, so... oops. So they, in a sense, learn from each other. There's a couple ways they learn from each other. One way is that genetic information is flowing through the population that you're watching. So yes, they're running around and stuff, and they don't like go off to the side to mate with each other or something. But they don't have to, because behind the scenes they actually are mating with each other. So they're just taking their DNA out, causing it to mate, and then dropping babies into the world. So in some sense, there's a transmission of learned knowledge through the generations. And ancestors are actually living in the same population as their descendants at the same time. And so you are seeing information traveling sort of forward in time in that way. The other way is that they affect each other. So, like if there is some subpopulation of agents that like to just stand there and block everyone, then the ones that want to go around there are basically implicitly being affected by the behavior of their peers. And so that will cause in some kind of group dynamic in what you call maybe in biology an ecology, where they'll be forcing each other into different niches through their interactions. And so in that sense, they have an influence on what each other learn. But what they don't do is they don't explicitly talk to each other. One individual doesn't say to this one, hey, I figured something out, like maybe you should do that. Over their lifetime, they have static brains. Basically, they're born the way they're going to be. It's all instinct. And they all die exactly the same as they were born.
Question.
Yes.
How is the starting population selected?
The starting population, like I said before, is random brains. So just random neural networks. And you'll see that in a second, actually, what that looks like. Completely randomized, small networks, because it's neat, so it starts with very small networks. And basically, as you'll see, they're not very bright. They kind of run around and look like people who have no brain. So you get to see that in a second. But does that answer the question?
Yes.
Yeah, so from that, some will be better than others. And you'll notice that too. It's very fast, so you gotta pay attention to catch this. It bootstraps very quickly off those that are better, because there is statistical variation. And so then you'll start to see them getting smarter quite quickly. So what I'm going to do, this is Nero, I'm going to go into a training scenario and start from scratch, which means from the randomized starting population. This is called the sandbox. It's a training area. This is the enemy. We call this the enemy. This is just a dummy. He can't be killed. He's just going to stand there. He's not going to shoot anybody. He's just for target practice. Now, what we're going to do is we're going to drop a population in here and have it learn. They don't know anything. They don't know what even, they don't even know what this thing is. So they've never seen an enemy before. And so they're just totally random neural networks. And so what I'm going to do is I'm going to give them what I want them to do. So that's what these things are. These are sliders. This one says, if you can't see this, it says approach enemy. What I'm saying is approaching the enemy is very important. I could also say don't approach the enemy, but this means do approach the enemy. And this is a hit target slider. So I could say this is a little less important. So the most important thing is to learn to approach. It's obviously an important tactic in a battle. And the second most important thing is to hit the target. Now, these are interesting things, these sliders, because you may think these are commands, like I'm telling them what I want them to do. That's not actually true. This is actually the fitness function. I'm saying that if you do these things, like if you get close to the target, you will get a higher fitness than someone who doesn't get close to the target. This information is never transmitted into their brains. They don't receive this like a command. And so it's just the implicit selection pressure that's going to cause them to obey, or to learn to do this. So they're going to have to learn to actually do this and to satisfy these criteria. So what I'm going to do, So is I'm going to launch them, and I'm kind of warning you here because things happen fast. I want you to be able to see what it looks like. I guess I can allow sound to go. And so, you know, student-created soundtrack and so forth. It's a totally student-created game. And I'm going to launch the team, and you just look at it quickly before it starts to change. So you can get a sense of what life is like with no brain. This is what the cafeteria would look like. Okay, so, whoops, I gotta get myself, now, I think I put this enemy too close. Let me back a little. Okay, so what we're seeing here is there are some individuals that are attracted to this enemy. You can see them over here. They are attracted because their neural networks happen to tell them to move forward when they see the enemy in a particular zone. And these guys are literally having higher fitness because of these slider settings. Okay, now there's some individuals that are not too bright, like somebody over here, just on vacation or something. But those individuals are having a low fitness, so they don't look good from an evolutionary perspective. Now, the interesting thing here is what you're watching is evolution happening in real time. In other words, these individuals here are having children, and they're falling in from the sky here. We call this area the factory. And these individuals who are acting silly like this one are not having children. Genetics are not actually persistent. And this causes pressure, of course. There is selection pressure on the population. So in a matter of minutes, you actually get robots that can follow their sensors. And of course, this is not programmed behavior. And I want to show you, convince you that this is true, that this is a truly evolved behavior by taking possession of this guy and moving it around. And as you can see, it's like playing with ants. So they start following him around. And this is a result of evolution. And in fact, what I'm doing right now is training them. This is putting more selection pressure on them. Because of course, the ones that get to me the fastest are the ones that get the highest fitness. So this is a really actually desperate situation. You don't get here fast enough, you're never going to have any progeny for the rest of eternity. So you better follow me. And so I'm actually training them by doing this, and they get better at following me. And okay, so we can say at some point that we're satisfied. Now, you're never going to get absolute uniform perfection in the population. There's always going to be somebody like this out there. Why is that? It's because there is a cost to exploration. I mean, in other words, what's happening in evolution is essentially exploration. We're looking at different points in a space of possibilities, which we call the search space. And we cannot explore that space of possibilities without being willing to sometimes do something that doesn't work. And so because there's mutation happening, there will always sometimes be someone born who's essentially not able to do the task. And that's just the cost of exploration. Of course, we could just artificially cause it to converge or kill that person off or something like that. In fact, we can do that. So, like, if I don't like this guy, I don't like his attitude, you just smite him, and he's going to blow up, and so we won't have his genetics are now gone from the population. But someone else like that will eventually appear. Now, let me show you. This is something we could do. Now, the point of this game is to make things get more and more complex. So I want to train them to get better. This is like a really rudimentary military tactic, of course, just running towards somebody, shooting them. So I could say, okay, let me do something, and this is going to be the equivalent of like an asteroid hitting the Earth and like, destroying the dinosaurs. This is an absolute cataclysm. I'm going to put an object here. There's a wall. And no one has ever seen a wall before, right? They don't know what this thing is. So those who were once great now are nothing. They can't get to the enemy because they haven't dealt with walls. And so, once again, selection pressure takes hold because some of them will have a slight tendency, like say, if they're lucky near the corners, to go around that corner, where some won't. And evolution will pick up on that. And it'll notice that those ones are the ones that are getting around the wall. And over time, it will begin to evolve more and more individuals that can go around the wall. And in this case, you're seeing that there's two strategies for getting around the wall. There's this way and that way. There's very too much noise. And so eventually they'll get good at going around the wall and get more intelligent in that way. And then I could do, like I could add things in, like I could say, let's put in something we call a brutal turret. This is another disastrous situation that I create. Now, I'll add a turret over here that tries to kill them. And this is another kind of cataclysm. Now, they're trained to go to this, but this thing shoots them. So I could tell them, avoid fire. So then I can make that a big priority. And now they'll evolve eventually to avoid fire. But of course, for a while, they're just going to get slaughtered because of what's happening over here. But eventually, they'll start avoiding this situation. It's just another kind of cataclysmic situation. That gives you a sense of how training works. I don't want to actually sit through the whole training of a sequence because that'll be the whole talk. And instead, what I want to do, I want to show you how smart they actually can get. Just to show you how powerful this kind of algorithm is. And so, I'm going to load up a team that was already trained and show you it acting. This is a navigation area. This was trained up just like you saw. There was a team that was trained, in this case, to go to this flag. So instead of going to the enemy, there's an approach flag goal. And then the trainer put like a wall, and they learn to go around the wall and get there, and then they just put more and more walls until they had a whole maze. So they actually evolved completely functional maze navigators from scratch with no pathfinding algorithm or anything like that. They just evolved their brains, so there's neural network control on it. And we put another criteria in here to make it even harder, which is we said don't stick together. So that means that they can't all just go the same path. They actually have to cover the whole maze and get through the maze because they're not allowed to stick together, or else they'll get penalized and they won't have children. I'm going to turn off evolution because we already trained them, and just launch a team and kind of see what the solution is. Now, this was trained in about 1 hour by an undergraduate. So what's interesting is, this is like somebody's doing machine learning experiments without knowing anything about machine learning. And this is a kind of a sophisticated experiment that this undergraduate ran. The undergraduate doesn't know anything about neural networks or machine learning or anything like that. And so this is kind of cool about this kind of an interface, is that it allows you effectively to run these kind of things without actually knowing what's going on under the hood. So what's going on here is you're seeing things like that. Some of them will go around this wall twice because they're waiting for traffic jams to free up over here. Because they're not supposed to all go together. And so actually it's a quite sophisticated behavior that we're seeing, where they try to spread out and at the same time get to the flag at the end of the maze. Okay, the last thing I got to show you here, of course, is a battle, because that's probably what you want to see. So I'll show you a battle. These are teams trained by undergraduates that have different strategies. So you'll see how you can have different strategies. So we'll take the Grove Grocers and Death from Afar teams. And they'll fight it out in the Shadow Grove. So these different arenas here. Okay, so you can see the situation here is that there's a big wall. That's basically the issue in the Grove. There's the two teams. They've been trained to deal with this kind of situation. So they both understand that they can't fight through that wall. But you'll see that there's a big difference in their strategies as they clash. So coming around the wall is the Grove Grocers. In Death from Afar, as you can see why it's called Death from Afar, is it likes to hang back. And actually, that can be a tricky strategy. It may seem like being a coward is not such a good thing, but it's hard to hit a moving target. And so actually, and these guys are running backwards, of course, probably not a real-world strategy that you see very often. But if sometimes it can be difficult to get these Death from Afar guys. So Death from Afar are the red team, and in fact, in this case, Death from Afar is winning. You can see that there's only 4